I have estimated, according to the number of hours that we have done, we have left with 4 hours, including those of today. And which means that there is likely no room for doing Wilson's renormalization approach, which usually, however, is an approach I tend not to deliver to the students, to ask to the student in the exams, because I have experienced that students tend to have problems with Wilson renormalization group because it's a somewhat more advanced field theory methods. That's in the past, I've always found that, you know, I ended up putting students a little bit in trouble while doing this. So I decided, you know, to keep it as a extra topic like the one we did on data science. So I guess there is no time to cover that because I need 3 lectures. But rather I'd like to devote the last 2 hours to a discussion on scientific directions, including those that are given in my group, but not only. There will be so there will be a mini conference in the last lecture by Potestio on different activities that concern statistical physics in Trento. So many people, including myself, Lattanzi, Tobiana, Potestio, and some guests, will have 10 minutes to tell a little bit about their research. And so if you're interested in a perspective research in statistical mechanics for complex systems and possible merging with quantum computing or with artificial intelligence, there's quite a lot of topic going on, and there will be this fantastic mini lecture organized by Raffaello tomorrow, actually. Are you aware of that? Do you want the link? I will put the link in our chat anyway. So everybody will have 10 minutes to sort of tell a story. That's a pitch, technically, not even a talk. I would like to devote a couple of hours to discuss more in detail what are the directions and to try to convince you that this is not a bad place where to go for further research activities, along with other very interesting topics across science, of course. I'm not claiming that this is any more relevant than anything that goes on in other fields, but so somehow today we're going to finish the real hardcore part of the course. And we're going to do that by touching on 2 topics. The first one is deepening what we learned from Landau theory, and in particular, understanding what can you extract from it in terms of predictable quantities. Because as far as, so let me just summarize the main results of last lecture. The main result of last lecture was that using Landau theory, meaning using a mean field approximation, we were arriving to this this result, which was basically stating that to mean field level, the Gibbs free energy as a function of magnetization could be estimated by taking the Hamiltonian of your system and replacing the field with this average value. That's why it's called a mean field, right? Because remember, this is the Hamiltonian. So this is the Gibbs free energy. This is the Hamiltonian. And now remember that M of X in general is the expectation of value of phi. And therefore, By this first result, we are saying that to mean field level, we neglect all fluctuations of the field, all thermal fluctuations of the field, and replacing the mean value and essentially calculating the energy at the mean value. So physically, this is more or less like having a partition function. The partition function, say in an harmonic oscillator, will be something like this. Let's suppose U as a simple structure. It could have a more complicated structure. Of course, there's an intrinsic entropy associated with this thermodynamic state, because this entropy, because basically x naught is the minimum point, but thermal fluctuations allow you to explore the neighborhood of this point, and that's what ultimately is called entropy, right? Now, if we do what we did yesterday, we approximate this with now this is what we're going to go further today. Remember, this was the Gaussian fluctuation. And we're going to rederive this for fields today. But the point that I want to make is if I now pull out the factor kt, I'll get something like u of x naught minus something which contains temperature and a function of x naught, which is this logarithm. And this function of x naught is precisely associated with thermal fluctuation in the well, right? And therefore, this is really Ts. And this is the free energy in terms of U minus Ts, right? So what this equation is actually telling me is that the entropy of my system is due to the thermal fluctuations around the minimum energy state. But in Landau approximation, I'm neglecting this contribution altogether. So to some extent, we are neglecting entropy. The entropy associated with the fluctuations of the field. And that's why if you go back here, you'll discover that we are replacing a free energy with an energy. Okay? Okay. So in the 50s, Landau and Ginzburg developed this theory, and Ginzburg was showing and critically analyzing when fluctuations become important, whether we have a criterion where we can have criteria for understanding what fluctuations are supposed to be important. And these are called the Ginzburg criteria, and I will not go into that too much detail. You find them well described in the, say, Lebella, for instance. But the point that I want to make here is that, very, naively, they're more or less based on the idea that you evaluate the average value of the fluctuation. Yes, if you can estimate the average value of that fluctuation, then the Ginzburg free energy. So the Landau theory breaks down when the mean field squared is compared to the mean square fluctuation, because that's when fluctuations become important. But okay, I leave this to those who are really interested in. But the second The second point that we really got out was a relationship between the magnetic field and how to obtain the magnetic field from the Gibbs free energy. And this was, the following equation was only true, the rest of this equation is only true for a constant magnetic field. So where the derivative was 0, if I had included the derivative, let me include the derivative. This was like, well, let me not include the derivative for now. The magnetic field was actually negative R naught M plus U naught 6 M cubed. So what we went through last time was that if I set this to 0, then I have one stable solution as long as this is negative, and then I start to have two stable solution in the case in which I pick up a negative sign here, showing that I have two degenerate magnetizations when the external magnetic field is 0. This is the critical temperature. This is temperature. This is magnetization. And this is the famous phenomenon of spontaneous symmetry breaking that is so central in basically all of theoretical physics. Now, of course, if I include the dependency on the position, then it is still true that this is the functional derivative of gamma with respect to m and x. Now, gamma is the integral at some dimension of m of x negative d slash 1/2 plus r naught half plus u naught 4 factorial magnetization square magnetization. And therefore, if I include this, the equivalent of this equation here will include also the Laplacian of the magnetization. So the magnetic field, depending on the position, will be negative Laplacian of the magnetization plus or minus R naught, depending whether I'm counting this to be always positive, in which case I have to put a plus and minus depending whether I'm above or below the phase transition, or I'm letting R naught change signs, in which case I will only have a plus, but R naught itself could change sign. It's completely conventional at this point. And then of course I have plus U naught over 4 factorial m square of x. And I think I have, sorry, there's an m square here. Of x. And I think, no, this m of x, and this is m cube f. Oh, finally got it right. It's basically this equation with an additional term that contains the Laplacian. And I think this is nothing particular deep, just applying this definition over here to our estimate of the Gibbs free energy. Now, how can we test this theory? And because you see, in order to discover that we could predict phase transition, we needed to make the assumption that R naught was flipping sign across TC, right? So that R naught is a function of temperature, and they can be positive. So that R naught is positive for T greater than Tc, and negative, if you want, for greater T less than the critical temperature. So in some sense, the theory was qualitatively capturing the emergence of two degenerate states. But the question is this theory predictive? Because in some sense, I have put the physics I want to describe by hand, assuming that R naught can change sign. Do you guess that? Do you get that? So now the question really arises whether we can indeed make predictions that can be tested against experiment. And in order to do that, we need to evaluate something different that can be tested against the experiment. And what we will concentrate on is, of course, a two-point correlation function. And again, you might claim, why don't we do that directly from the why don't we do that directly from the value from the original Landau theory? Of course we may, but we need to do that in a non-perturbative way, because across the phase transition we cannot simply estimate that partition function perturbatively. And what we are doing here is exactly using everything we have done to be able to compute that non-perturbatively. Okay, so I'd like to show you how you get the partition function. And the idea is very simple. First, we start from this functional differentiation. And then we say, okay, if I take one more functional differentiation, say with respect to m at point y, I'll get the double differentiation of the Gibbs free energy with respect to m at x and m at y, right? Now, the point that I want to make is that this guy here is actually the two-point correlation function to the -1. So stated differently, if I can evaluate this guy here, this double differential of the partition of the Gibbs free energy, I basically have already the inverse of the Green's function, and I can use that to evaluate the Green's function. And how do I do that? Well, first of all, let me define the Green's function. The Green's function, x or y, if you remember, is this object, right? Well, let me write this explicitly. Right? So it is clear that I can drop this extra factor, say x, by acting with the functional derivative with respect to the field onto this. So in other words, this can be seen as d by db of x of phi of y, right? So in other words, G is equal dm by dm x by dby. Oh, sorry, dmy by dbx in this case. And this is gxy. Now, from here, it is immediate to show that this operator here is in fact g to the minus 1. And you prove it by simply showing that g to the minus 1 times g is delta. Let me do it. Let me take the integral over y of d square of gamma dmx dmy, and then apply it to g, right? So I get dmy, and for instance, dmz. This is my g, y, z. And I want to emphasize that I'm summing over a dumb index here because this is basically a matrix vector multiplication, right? It's an operator. So y plays the role of the summation index, if you want, in the continuum. But now I'm using the fact that this is in fact dB x by dm y. Remember? And of course, here I have made a mistake. Here is B. Sorry. Of course, it's B. So you see, now things start to pile up because I get an integral in dy, dB of x, dmy, dmy, dB of z. So eventually I get dB of x divided by dB of z, and this is delta x minus z. So I want to summarize what we have done so far once you've done copying. First, I've basically introduced some results that are completely formal. The first result is this one, that B is d gamma by dm. And the second result is, of course, that the second derivative of B with respect to m, sorry, the dB by dm is the second derivative of gamma with respect to m. Next, I verified. The third result was that a two-point function can be written as dm by dB. And then I want to verify that this object is basically this object to the minus 1. How do I do? I simply multiply by them and see that I get a delta function. And if you use the results that I've basically outlined here, it's basically a trivial manipulation to show it. So in other words, if we have gamma, then we have g to the minus 1. And then, you know, if you have g to the minus 1 non-perturbatively, then we can get g by going to momentum space, invert, and then anti-Fourier transform. So I think at this point you might be confused because you might say, but we already know from the Wick theorem what is G, right? The Wick theorem tells you what is G. It's the propagator. But the Wick theorem is, strictly speaking, a theorem from a quadratic theory. Here, we are not dealing with a quadratic theory. We are dealing with a quartic non-perturbative theory. So computing the propagator for a quartic non-perturbative theory in the language of perturbation theory would correspond to summing all possible Feynman diagrams to infinite orders. And that's not something we can possibly do in a reasonable amount of calculation, in a finite amount of calculation. So really what we are trying to do here is to develop a scheme to get the propagator, even if we cannot rely on perturbation theory. Okay? And the idea is first evaluate the Gibbs free energy non-perturbatively. And we did that by means of the Landau approximation. And next, find a way to obtain the propagator from the Gibbs free energy. And that's what we have done now. So if you have the propagator from the Gibbs free energy, and we have the Gibbs free energy, then we have the propagator. But we had, since the Gibbs free energy was evaluated non-perturbatively, the propagator will be evaluated non-perturbatively. So what we really need to do is to take the second derivative of our gamma. So now let's go back to what was our gamma. Remember, our gamma now was the integral over some dimensions that we don't know. It could be 3 typically, but in general, these theories are developing an arbitrary number of dimensions, often for reasons that sometimes it's you know, taking the large dimension limit. So fine. Now let me not go into that. Let's say D is the dimension, and let's say the dimension is 3. Opening up, changing the dimensionality will open up a discussion that I'm not ready to complete in a finite amount of time. So I have my Gibbs free energy. I have my field. I have my, so let me get the complete result right now with all the factors right. Yeah, I get 2. Let me pull out the 2 here. So I will get like R naught plus, and I think this will be U naught over 6. Now it was 4 factorial, so 4 factorial, it's 4 times 3 times 2. So that's 4 times 3. And then I get let me do it down here. M of x squared. And then I get another M of x here. Now, when I act with my first functional derivative here, say with respect to my, I can act here or here, right? Well, in fact, I can also act here in 2 different ways, but let's forget this for a moment. Well, let me get just first the first 2 terms. I have 2 options, right? So this will kill the 1/2. However, When I also include the m to the fourth, the last term here, I have 4 options. So let me first say that d gamma by dmy, we already did this calculation, but let me do it again now because I would need it again, will be negative plus r naught plus u naught sixth m squared of y my. Now I act with the second derivative because I want to take the second derivative with gamma with respect to mx and my. And this will produce this time an operator, as it should, because remember, this second derivative of the Gibbs free energy with respect to the sources is going to be the inverse of a propagator. And the inverse of a propagator is an operator, right? So I'm getting this plus this. So let me pull out the delta function. So when I get dmy with respect to dmx, I get a delta function, x minus y. So I get, let me pull the delta function out here. And then I'm getting this plus r naught sorry, there was a 2 remaining here, plus u naught over 6 m. Okay? So the non-perturbative story has resulted in an extra term here, which in general is position dependent. But if I'm under constant magnetization, then we have discovered that basically g to the minus 1 is going to be negative or not plus r naught plus m squared. So basically what we have is an extra mass term in the propagator. Okay? And this is true across the phase transition. Now, given this fact, I can associate with this with a Yukawa mass, right? Let me call this small m squared. Okay? Do you follow me, guys? So my propagator g of x, y is going to be a Yukawa propagator. Not sure I have the pi factors right. Let me see if I have it on the Lebel-Lock. Let me see if I can get this on the, oh yeah. It's 1 over 4 pi x minus y e to the minus, and then I have m, this mass, which depends ultimately on temperature, and x minus y. So I can correlate the local magnetic, I can compute the local correlation between magnetization in 2 points. Now, it turns out that in linear response theory, you can compute, you can compute the scattering of the neutrons across say, a metallic lattice and relate that to a 2-point function. And therefore, by neutron scattering, you can measure these 2-point correlation functions. So all I want to say is that this is measurable. So the fact that, so basically, let's now look at what happens as I approach the critical temperature from above. As I approach the critical temperature from above, I'm in the no magnetization phase. My small m square is actually R naught square, right? But at the critical temperature, R naught vanishes, right? And m is vanishes. So at Tc, both R naught and m are 0, right? Which implies that this small parameter m squared is also 0. Because remember, m squared is the sum of R naught and m squared. So this is what is usually referred to the fact that at the critical temperature, the correlation length, the typical length of the exponential decay of correlation vanishes. Sorry, become infinite. The inverse correlation length, m squared, m vanishes. So lambda of Tc, which is 1 over m squared root of m squared of Tc, is actually infinite at Tc. So when you approach the second order phase transition, you're dominated by correlation that pervade macroscopic regions. That's what you're saying. And that's what you expect, because you start, the spins are no longer paramagnetically coupled. They start to feel each other across the system. And this is incredibly exotic physics, if you think about it. How can system become long range if the interaction is short range? So we have how can you develop long range correlation from a Hamiltonian that only has short range correlation? Can you appreciate why this is a Nobel Prize? Because it makes no sense whatsoever physically. You have a theory with a short range Hamiltonian, and you're able to correlate the system for macroscopic scales, macroscopically, by developing long range correlation. You know that Coulombic is long range, right? And the reason is that at the magnetic state, at the transition temperature, you are reorienting the structure of the vacuum, and you're propagating the correlation by changing the structure of your system, having all your system pointing in the same direction, which basically results in an infinite correlation. So this discovery led to the.
Sorry, could you say the last sentence one more time?
Yes, sure. I'm not sure I have anything to offer. I mean, basically what this result is telling you is that the change in the structure of the vacuum provides the substrate for maintaining correlations at infinite distance. And the vacuum changes you because you start developing magnetization, and once you have magnetization, you're basically correlating the direction of the spins across the system. But you cannot do it in a paramagnetic phase So in some sense, the change in structure of the vacuum has highly non-trivial consequences. And this was so seminal in theoretical physics. So let me ask you a question. What is the mass of a proton? Roughly speaking, in GeV, do you know? Anyone? Rule of the thumb.
940 GV.
1 GV. 940 MeV, 1 GV, okay? Roughly speaking. So if you open the particle data book, what is the typical mass of U on D quarks? Order of magnitude. Do you know?
Oh, about 100 MeV.
Absolutely not. It's about 10 MeV or less, depends on the estimates. Now, nobody has seen a quark and put it on the balance, on the weight measurement. So estimates vary a little bit as precision estimates of non-perturbative QCD change, but we are in the ballpark of 10 MeV. So that's what, so those 10 MeV are those generated by the Higgs. Remember when you hear the sentence, the Higgs is providing the mass of the fields. That's okay for quarks. It provides those 10 MeVs. Of course, it provides much more for the heavy quarks, but let's not worry about it. So if the quarks are 10 MeV, where does the mass of the proton come from? Okay, have you ever thought about that? When you learn istituzioni di fisica teorica in fisica nucleare subnucleare, you learn that the quarks are roughly 300 MeV. That's the quark model. These are not the quarks of QCD. The quarks of QCD have 10 MeV. And I'm telling this that has nothing to do with Landau theory because it has to do with Landau theory. Otherwise, I wouldn't be telling you. Because basically, in the vacuum of QCD, something very similar to what happens in ferromagnets is going on. There's a critical temperature called the chiral symmetry breaking temperature. Below and this temperature agrees numerically with the deconfining phase transition temperature. So basically, the two must be related. We don't exactly understand why. I think now people are beginning to understand, but there might be a connection between the two, and at least in some model, a connection becomes emergent. But below this temperature, the vacuum changes structure. And in particular, you develop a finite magnetization. And the magnetization is no longer spin magnetization, and is another observable, which is the so-called quark condensate. So let's call this phi, which is basically the density of a quark-antiquark pairs in the vacuum. So the vacuum changes, goes into a Mexican hat where you have a finite amount of quarks and gluons floating around. So, you know, G square and psi bar psi are no longer zero. I finished my. So the vacuum is a little bit like a ferromagnet. And the result of this vacuum is that the quark propagator, just as this two-point function, develops, guess what, a mass at the critical mass. And that mass is, roughly speaking, 300 MeV. So the quark model quarks are the result of adding the effective mass due to the breaking of structure of the vacuum, symmetry breaking in the vacuum. And they go from 10 MeV to 300 MeV. So I don't expect you to remember any of this. I'm just trying to tell you how deep and seminal these ideas are in theoretical physics. And it goes along. So superfluidity is something like that. Superconductivity is something like that. And I could go across the entire field of area of science, keeping up, finding examples in which symmetry breaking like this takes place. Okay. So I don't want you to study this, but I want you to appreciate how relevant it is across physics. And also cut the bullshit talking to the pop science, saying that the Higgs boson is providing the mass of particles, because only 10% of the mass of the proton is due to the Higgs boson, even less. Everything else comes from quarks, from the structure of QCD itself. In other words, if in QCD the masses of the quarks were completely massless, you will still have a proton of about 800 MeV. Which means basically all the energy, all the mass of the proton is storing the energy of the gluons inside it because of Einstein m=mc² relationship. There are gluons in the proton keeping almost massless quarks together. These gluon fields have an energy because, hey, they are electromagnetic fields with a color, so they must have an energy. And the energy in unit of c² is the mass of the proton. Cool, isn't it? So I'm telling all this to say spontaneous breaking is a phenomenon that not only concerns those who are interested in statistical mechanics, it basically pervades all fields of science, and it's extremely important in quantum field theory. People claim that the solution of the strong CP problem is due to spontaneous symmetry breaking. The asymmetry of baryon matter antimatter is due to some kind of spontaneous symmetry breaking. Certainly, the Higgs mechanism is a spontaneous symmetry breaking. The mass of baryons is mostly due to this spontaneous symmetry breaking. Okay. So that was it for the first part of the class. Let me go into the second part of the class and to evaluate explicitly Gibbs correction. Now, the part of the 2-point functions is not on the notes, but is on Lebellac's book, chapter 2. You find all about it. Okay, so you basically find all this material there laid out for you. Now I'm gonna stop recording for a second. Okay, back to recording. I didn't want that to stay on tape. Okay. Okay, so we need to go back and evaluate the partition function to next level. So remember, we have our fields. Now I will call this W of phi and B, where W is nothing but the famous H minus B phi, right? I'm using the notation W to be consistent with the notes I have online. This is the partition function as a function of B. Now, let me repeat the idea of the saddle point approximation. We take W, we differentiate with respect to phi, we find a solution which will depend ultimately on B of the static condition. And we expand this around phi bar. So this would be phi bar of B. There's going to be no linear term because we are in the static point, in the saddle point. And now we have the quadratic term. Now, in the quadratic term, I make the claim that I try to convince you for in a minute, that this will involve a double integral. Why is this a double integral? Because remember, fields are basically, the position of a field is a label. And if I discretize on the lattice, I have to, I have every single of these functional derivative becomes a partial derivative over a different variable, and I have to sum over all the different variables, right? So when you do second order Taylor expansion of a functional, you get double integrals. Okay? Are you confused with this? Okay. Now, let me call this difference psi of x, psi of y. So I can always shift variables, and my z will be e to the negative w of phi bar times, now I'm going to write explicitly the correction. I have a path integral over psi e to the negative 1/2 integral dx integral dy psi of x. And then I'm going to have this weird second order term evaluated in psi bar, psi of y. As usual, when I get a function and I differentiate it twice, I get an operator, right? So this is an operator. So all in all, this is a Gaussian integral of the type that we have learned to deal with. And I think I'm not gonna surprise you if I tell you that, let me look at this guy. And this guy is once again up to an overall delta function of x minus y that I can pull off here. And that's going to be minus negative square plus r naught plus u naught half phi bar of b square, because remember, I have to evaluate this guy at phi bar. Now I'm left with evaluating this integral here, which is Gaussian, but we never actually went into estimating what it is, right? To evaluate exactly what it is. Well, we know that for a single Gaussian, integral in dx e to the minus x squared over 2 sigma squared, that's going to be a root of 2 pi sigma squared, right? But here we have something different. We have an integral over, after discretization, a number of variable xk, and the exponent contains a non-trivial bilinear combination. I'm using Einstein notation here. I'm using Einstein notation. Every time you see two indices that are repeated, you implicitly assume they're summed over, okay? Now, the claim that I make that the multidimensional generalization of this result will involve the determinant of O. Well, how do I know? Well, again, let me take this x, O, xi, O, xj, right? This is the matrix elements of O, and then I have, in other words, let's take this and let's diagonalize this. So there is going to be a basis, let me call it BK, which are some change transformation over XK, right? So if I look at this as a vector, the X as a vector, X1, Xn, and O is a matrix, then O is Hermitian, can be diagonalized, right? By a unitary transformation. Okay? The fact that it's unitary means that if I change variable from X to B, I don't have any Jacobian in the integral. So if I do that, this integral becomes integral over K dBk, and the exponent now is going to be negative 1/2 sum over K. Now I put explicitly BK squared half lambda K. Because I've diagonalized this bilinear now. And now you see that after you have pulled out a diagonalization of it, then now all the Gaussian integrals are decoupled and you can evaluate independently, right? So you basically lambda K plays the role of a 1 over sigma K square, right? So you can evaluate all of them and you basically get that this is 1 over root, sorry, yeah. Of the product, so basically is the product of n Gaussian integrals and that's basically 1 over root of the determinant, because I get the product of the root of the product, determinant of the operator O. Sorry, okay, that enters here, right? So this means that my Z functional as a function of B is is up to an irrelevant constant. This is e to the W phi bar divided by the root of the determinant of the operator dB of phi bar. And I can write this way. Negative 1/2 trace log D. Well, the sign, I'm a little, yeah, phi bar. I'm using the fact that determinant of A, e to the trace log A, right? Do you know this relationship? No? Well, this is trivial if you imagine that the trace and the log and the determinant are both invariant under basis. So you can do that in the eigenvalue basis, in the diagonal basis, in which case this is trivial, okay? Fine. Now we have this very nice looking relationship. we are left to evaluating trace log, because this is a formal expression. We want to have an exact expression, okay? Something you can put on a computer. So let me begin by saying I will be a little bit sort of okay. Let's stick for a moment to this and say, okay, this is Z. Now I can, so the basic idea here is to say that this is essentially everything goes as if there was an effective term in the exponent, which includes all this with a correction. So now I can do the same Landau trick, but not replacing the Hamiltonian at the saddle point, but replacing the effective Hamiltonian at the saddle point, okay? Because after all, it's everything goes as if I had a slightly different Hamiltonian, right? Because I've computed the corrections to the Hamiltonian due to the fluctuations. So if you do that, then you have a effective magnetization which is the effective Hamiltonian computed as a function of magnetization, so effective free energy. So gamma effective free energy is going to be the Hamiltonian as a function of this plus the corrections, which is 1/2 trace log d as a function of magnetization. And now we are left with the problem of computing this. If we can compute this, then from this we can get the correlation functions, including the effect of correlations of fluctuations. And now I'm going to be a little bit sloppy, and that's how Lebellec does it. But I think it's okay. So I'm using the fact that the logarithm of d is the sum over k minus 1, k to the minus 1, d minus 1 to the k over k. That's a Taylor expansion analytic expression of the logarithm. So that means that you can evaluate the trace term by term and resum. So when you evaluate the trace, you use the linearity of the trace, you pass it through. So in other words, you first evaluate the trace of d and then you resum this. Okay. Now the trace of d, I can use any basis to evaluate it. I use the momentum basis. Of course, this must be regularized somehow because this is a divergent integral. And you have to go through the regularization procedure. But then this is the sloppy part if you want. Trace log of d of m ultimately becomes integral regularized. So now we have a small logarithmic correction two correlation functions. And you can use these corrections to compare to experiment and understand the role of fluctuations around the mean field for your systems. So this procedure that I've just used, that is the fact that you treat. So let me once again go through the ideas that we followed in this lecture. Then the technicalities, you can go through the notes and you find them all laid out. And then if you don't get them from there, you go to any quantum or statistical field theory book, including Lebellac's, and find it laid down even more in detail, okay? But the idea basically here is, first, I understand the mean field behavior. Then I go one next order in the Taylor exponent expansion of the exponent. It's going to be a functional Taylor exponent because these are fields in the continuum limit. But at this point of the course, you should not be scared of the functional Taylor exponents, right? Functional Taylor expansion. So I go to the next order, the quadratic order. Now, at the quadratic order, I will get a Gaussian integral with an operator, which is the second derivative of the functional at the critical point, at the saddle point. Now, this is a Gaussian integral. It's basically an integral of a Gaussian bilinear, because the operator is not just diagonal, it's an operator. But then it's straightforward to understand that you can compute this, because it's basically the quadratic fluctuation only result in a 1 over the determinant factor. Now, the determinant of an infinite dimensional matrix is infinite. And that's why you need regularization, ultimately. But nevertheless, after regularization, this means that you have a determinant which includes fluctuations around the mean field. Now, if you exponentiate this determinant, it will provide you correction to the mean field estimate. And if you put together the mean field estimate and its correction into a single functional, you get a single functional whose functional derivative will give you the correlation functions, including the corrections. Now, in this case, we are talking about thermal corrections, right? Now, this concept, this effective Hamiltonian, is the Hamiltonian whose mean values will provide, who is the effective Hamiltonian whose functional derivative will ultimately provide the correlation functions, including the effective fluctuations. Now, exactly the same procedure can be transferred in field theory, and guess what? It is called the effective action construction. If your theory has a non-trivial vacuum, then of course it means you have a non-trivial saddle point of the energy of the action. So what you want to do, you want to expand around this saddle point and include quantum fluctuations around it in the form of an effective functional. So in the end, the effective functional construction in quantum field theory automatically will give you correlation functions, including the effect of quantum fluctuation to quadratic order, just as much as the effective Hamiltonian of Landau-Ginzburg theory will give you the correlation functions, including quadratic fluctuations at the thermal level. So I'm going through this to tell you that these tools are the same in quantum field theory and statistical field theory. You have a dictionary. And if you do some sufficiently advanced quantum field theory, you will have to deal with effective action construction in quantum field theory. And the theory behind it is exactly the same as the theory we have discussed here in the case of the Landau-Ginzburg theory. It's just a dictionary translating Hamiltonian into an action, a statistical field into a field that enters a path integral after quantization. But everything goes on the same. So this, if you want, the statistical field theory part of the physics of the statistical field theory is probably more useful for you as an addition to the quantum field theory course than is a purely statistical mechanics course. Okay? And okay, I think this will complete my excursion in statistical field theory. There will be so much more to discuss, but I'll stick to this for this course. I think this is a very long way we went through, from path integral in quantum mechanics all the way to effective actions in statistical and de facto quantum field theory. I hope this was understandable even from remote. This is the last time, hopefully, we do this course on remote. It is really bad to do it on remote, but this is a problem we all had in the past, in these 2 years. But in case anyway you got lost, of course, you're welcome to contact me over the next months to go over the details of it. And I think the fact that I have notes now quite extensively spelled out, available for you, should help you go through things, even if we've done it on remote. Do you have any final questions about everything we've done before we sort of reconvene next week?
Maybe I have one. Do
Yes.
you hear me?
Sure.
Last time, when we saw the effective field theory on a lattice, we say that basically the size of the single cell set ultraviolet cutoff.
Yeah.
Don't we have an infrared cutoff due to the fact that at the end we will always deal with the affinity length of our box of simulations, say, even if we impose the periodic boundary conditions?
You're absolutely right. You're absolutely right. The theory will have an intrinsic ultraviolet and infrared cutoff. And you want to beat them off. So typically, in many cases, for instance, lattice QCD, you have to fight with both. And let me give you an example where this cutoff can sort of why you need to fight making the lattice spacing as small as possible and the box as large as possible. Now, like I said, you always have, this is a regularization. At some point, you will have to renormalize, okay? And what does it mean to renormalize? To take your coupling constant, for instance, that you have in your actions, and match it to the one you have from experiments, right? So how do you get the coupling constant of QCD from experiment? This is not something you get like in QED. It's simple. You take two charges far apart, you measure the electric charge, and that's your E squared over 2 4 pi, right? But you cannot do that in QCD, right? You cannot take two quarks, put them far apart and measure their force, because they will generate quark and anti-quark and break the string. So what people do, they use parton distributions, high energy scattering experiments, and they look at the, you should be familiar with this. You know what are the parton distribution, right? And you know that parton distributions have an intrinsic Q-square dependence. They depend on the exchange momentum of the electron with a sample. And you can predict how parton distribution from the simple parton model, in which quarks are basically frozen when they get a photon, to one in which you get the effect of gluons and pairs, and you can predict these corrections as long as the momentum is sufficiently large for the coupling to be sufficiently small so that you can use perturbation theory. So this is all to say that we know the coupling of QCD, but we know it only for large Q square. So in order to regularize the theory, I need to make the cutoff sufficiently small that I can match it to the value that I know, and that is at large Q square. So I need to have small couplings. And in fact, typically, perturbation theory in QCD, let me tell you, breaks down somewhere below 1 GV. And if you look at what is the inverse of 1 GV, you know, delta X, delta P, or the H bar, right? In natural units, H bar is 1 and P is in GV. What is delta X? It's typically 1 over delta P. That is typically 1 over, say, 1 GV. And what is the inverse of 1 over 1 GV is basically 0.2 Fermi. So if you are a little bit more generous, you go to 2 or 3 GV, you get 0.1 Fermi. So at least you need lattice spacing of 0.1 Fermi. Okay. Now, suppose you want to study a typical strong interacting system. Tell me one system that you could study with QCD. Non-perturbatively. What would you like to study with QCD? For example, the mass of the proton, the simple thing that I can think of, right? A hadron. Because that's where non-perturbative QCD becomes important. Now, in order for this to make sense, you need to have sufficiently many of these cells for a hadron to fit comfortably inside. Okay, so what is the size of a hadron? What's the size of a proton in Fermi? I'm asking you because you need to know the basic scales of physics. All across physics. Chemistry, electron volt. Atomic physics, electron volt. Chemistry, say milli electron volt. Nuclear physics, keV or MeV. Hadron physics, GeV. And then sizes. Fermi, sub-Fermi. You know. So typical proton, let me tell you, is slightly less than a Fermi in radius. Okay? So you need to have many. And also, you see, you have to be careful because say you want to measure the mass of the proton, it means measuring the mass of this configuration. If your periodic boundary condition, you get another one here and another one here, right? Everywhere. Now, if these are not far enough, you're going to get pion exchange between these two copies of themselves. So in principle, you want to have boxes that are large enough for the 1 over m pi to for the Coulomb for the Yukawa interaction to go off. So you see, if you don't do that, then you're gonna expect errors coming from this infrared divergency, the infrared effect you just discussed. So just to give you an idea, when I stopped doing lattice QCD almost over a decade ago, typical numbers were like A was of the order of 0.1, now maybe sometimes 0.05. And the number of lattice points was of the order of 60 per unit, 64 per units. So that was 6 Fermi. So now you see infrared and ultraviolet divergence are there. And then ultimately what you do, you look how things change when you change them, those scales. And if you're in the confidence regime, you shouldn't change it. So typically, when people were doing renormalization on the lattice, instead of sending the cutoff to infinity as you do in an analytic calculation, right? At the end of the calculation, what you do, you measure things in units of 1 over A, sorry, in units of A, and you get some calculations on the lattice with an intrinsic stochastic error because you're doing Monte Carlo, and then you extrapolate, and that's your prediction. And of course, you do the same with lattice spacing, and you get like 1 over L, and then you get numbers, and then you hope to be able to make a prediction. So yes, you're right. And it's an active field of research trying to deal with this. Okay?
Okay, thank you.
Ci vediamo. Vi lascio il link sul Telegram per la lezione se siete interessati a quello che fanno negli altri, parte del gruppo SBP. Siamo un gruppo molto coeso, nel senso che ci piace che i nostri studenti sappiano cosa fanno anche i nostri colleghi del gruppo. Così possono scegliere cosa vogliono fare meglio per la tesi. Noi pensiamo che l'interesse del gruppo sia avere il maggior numero di studenti entusiasti possibile, non l'interesse del singolo PI di avere uno studente in più. Per cui vi suggerisco caldamente di seguire la lezione di Raffaello domani. Se vi interessa, se sapete che volete fare altro e non vi interessa sapere cosa facciamo, va benissimo così. Non è che tutti devono essere interessati a quello che facciamo. E io parlerò un po' più diffusamente di cose che magari mi riguardano più o meno da vicino nell'ultima lezione, e farò un po' di discussione in generale su aspetti interessanti che hanno a che vedere col corso. Va bene? Buona
Scusi,
serata.
Professore, mi sono perso. A che ora c'è questa cosa?
Mando i dati su Telegram.
Ok, va bene. Va
Grazie.
bene, grazie.
Ciao.
Buona giornata.